In 2000, the Clay Mathematics Institute announced 7 unsolved problems and offered $1 million for each. 24 years later, only one has been solved. The other 6 remain open, including the one that many mathematicians consider the deepest question in all of computer science. It's called P versus NP, and it asks something deceptively simple. Are there problems that are hard to solve but easy to check? The answer, yes or no, would transform everything. Imagine you're handed a jigsaw puzzle with 1,000 pieces. Assembling it from scratch takes hours. But if someone hands you the completed puzzle, you can verify in seconds that every piece is in the right place. This gap between solving and checking is the heart of P versus NP, and it shows up everywhere. A chess position, a protein that might cure cancer, an encrypted message, a delivery route. In each case, checking a solution is fast, finding one is another matter entirely. The question is that gap real, or is it an illusion? Let's be precise. In computer science, we classify problems by how long they take to solve as the input gets larger. P stands for polynomial time. A problem is in P if a computer can solve it in time proportional to n, or n squared, or n to the 5th, any fixed power of the input size n. Polynomial time is considered fast even n to the 10th power is workable. In principle, examples of P problems: sorting a list, finding the shortest path between 2 cities, determining whether a number is even. These are tractable, no matter how large the input. We have efficient algorithms. P is the land of the solvable. NP stands for nondeterministic polynomial time. A problem is in NP if, given a proposed solution, you can verify whether it's correct in polynomial time. Here's the key. NP doesn't say solving is fast, it says checking is fast. Classic NP problems. Given a set of cities, is there a route visiting all of them under a certain total distance? Given a collection of integers, is there a subset that sums to exactly 0? Given a logic puzzle, is there a set of true, false assignments that satisfies all the rules? For each of these, I can hand you a proposed answer, and you can check it quickly. But finding that answer in the first place? That might require trying an astronomical number of possibilities. Here's what makes P versus NP so tantalizing. P is a subset of NP. Every problem you can solve quickly. You can also check quickly. Just solve it and verify your own answer. So P is inside NP. The question is whether NP is inside P. Does every problem with a fast checker also have a fast solver? Or to put it starkly, if you can recognize a solution quickly, can you always find one quickly? Most mathematicians believe the answer is no. P is not equal to NP. The ability to check doesn't give you the ability to solve. But, and this is the humbling part, nobody has been able to prove it. You might wonder, why is this so hard to settle? Surely we could just look at a really difficult NP problem and show that no fast algorithm exists. For it, the problem is that proving a lower bound, proving that no algorithm can do better than exponential time, is extraordinarily difficult. You'd have to reason about every possible algorithm, including ones we haven't invented yet, every time someone finds a clever new approach to a hard problem. It might be the beginning of a breakthrough. And there are thousands of NP problems that are computationally equivalent. Crack 1. Crack them all. This equivalence class, called NP-complete, was discovered by Stephen Cook in 1971. It makes the problem both more beautiful and more daunting. Cook's theorem established something remarkable. There exists a problem, satisfiability, or SAT, such that if you can solve it in polynomial time, you can solve every NP problem in polynomial time. Richard Karp then showed that 21 different real-world problems are all nitrogen monophosphide complete. all reducible to each other in polynomial time. The traveling salesman problem, graph coloring, clique detection, knapsack packing, scheduling, all of them equivalent in computational difficulty. This web of equivalences means that P versus NP isn't just an abstract question. It's a question about the fundamental limits of efficient computation. And a solution to any one nitrogen monophosphide complete problem would collapse the entire class. Suppose P equals NP. Suppose someone, tomorrow, found a polynomial time algorithm for SAT. The consequences would be almost incomprehensible. Every encrypted message ever sent would be vulnerable, because cracking codes is an NP problem, and fast checking would become fast cracking. Modern cryptography, the foundation of internet security, banking, private communication, would collapse. But also, drug discovery could happen overnight. Machine learning would become exponentially more powerful. Mathematical proofs might be generated automatically. Complex scheduling and logistics problems that currently consume enormous resources would become trivial. P equals NP would be the greatest intellectual event in human history. And the most destabilizing. Most mathematicians believe P does not equal NP. And if they're right, it means something profound. Some problems are intrinsically hard. There are questions that checking can never replace solving. The gap between recognition and discovery is real. This would validate our intuition about creativity. Finding a proof isn't just checking a proof. Composing a symphony isn't just recognizing a good one. Solving a hard problem requires genuine search. And no shortcut exists. P not equal to NP is the version where cryptography stays safe. Where hard problems stay hard. Where ingenuity and effort remain the only paths through the labyrinth. P versus NP is on the Clay Millennium Prize list. $1 million awaits whoever resolves it. But the real stakes are deeper than money. The question touches on the nature of mathematical truth, the limits of automated reasoning, the relationship between discovery and verification. Can you always find what you can recognize? Can cleverness be mechanized? Is there an inherent asymmetry between creation and criticism? We don't know. The question remains open, as it has for more than 50 years. The hardest problems, it seems, are not always the most exotic ones. Sometimes the hardest questions are the ones we can state in a single sentence.